The universe is an ocean of unanswered questions. At the very edge of everything we can see, where light itself begins to fade into the primordial dark, lurk the most ancient and powerful objects in existence, the most distant black holes. These are not the quiet monsters of our galactic neighborhood. They are behemoths from the dawn of time, governing infant galaxies when the cosmos was a fraction of its current age. By the end of this journey, you will understand 50 incredible facts about these cosmic titans, revealing how they shaped everything we see today. We will confront a baffling paradox of their impossible size and uncover how they act as lighthouses illuminating the universe's first chapters. What does the edge of reality truly look like? The term most distant carries a profound weight in astronomy, one that fundamentally reshapes our understanding of observation. When we speak of the most distant black holes, we are not simply describing a location on a map of space. We are defining a moment in time, because light, for all its incredible speed, takes time to travel the vast gulfs between galaxies. Every glance into the cosmos is a look into the past. The light from our own sun takes about 8 minutes to reach us, so we see it not as it is now, but as it was 8 minutes ago. Now, stretch that principle across the entire universe. The light from these incredibly remote black holes has been journeying toward us for over 13 billion years. This means we are not seeing them as they exist today. We are witnessing them as they were in the universe's infancy, a mere few hundred million years after the Big Bang itself. This gap between when the light left an object and when we finally detect it is called look-back time. The greater the distance, the further back in time we see. So, the most distant black holes are our most direct windows into the conditions of the primordial cosmos. But how do we actually measure such an unimaginable distance? The universe itself provides the tool. As space expands, it stretches the very wavelengths of light traveling through it. This stretches visible light toward the red end of the spectrum, a phenomenon known as redshift. Think of the sound of a passing ambulance siren, how its pitch drops as it moves away from you. Light behaves in a similar way. The more space has expanded between us and the source of light, the more stretched or redshifted that light becomes. For these ancient black holes, their light is stretched so dramatically that it often arrives not as visible light, but as infrared radiation. Astronomers measure this redshift with a number denoted by the letter Z. A higher Z value means a greater distance and, crucially, a deeper look back into cosmic history. The most distant black holes ever detected boast redshift values above 7, placing their light's origin in the first 700 million years of the universe. So when we say most distant, we are really saying most ancient. We are using light as a time machine, and redshift is the dial that tells us how far back we have gone. This staggering distance has a name, a cosmic address for a point of light from the very dawn of time. The current record holder is a quasar known as ULAS J1342+0928. Its designation is a catalog number, but its story is anything but mundane. The light we detect from this object today began its journey over 13 billion years ago. To put that into a human scale, when this quasar first shone, our entire planet Earth did not yet exist. Our sun would not ignite for another 8 to 9 billion years. The Milky Way galaxy itself was still a chaotic, forming collection of young stars. The universe was a fundamentally different place, dense and hot and filled with the raw material of creation. We measure this incredible look-back time with a redshift value of 7.54. That number means the light emitted by this quasar has been stretched, its wavelengths elongated by the expansion of the universe by a factor of more than 8 times by the time it finally reaches our telescopes. We are seeing this object as it existed only 690 million years after the Big Bang, a mere 5% of the universe's current age. At its heart lies a supermassive black hole, a gravitational titan with a mass over 800 million times that of our Sun. The existence of such a colossal, fully formed monster in such a young cosmos presents one of the greatest puzzles in modern astrophysics. How could something so vast assemble itself so quickly? The light from ULAS J1342+0928 is a message in a bottle, cast into the cosmic ocean at the end of the universe's dark ages, and we have only just begun to decode it. That ancient light is more than just a beacon from the past. It is a detailed fossil record of a universe in its first chaotic breaths. By analyzing the specific wavelengths in the light from these distant quasars, astronomers can read the chemical composition of the gas that existed billions of years ago. This is because as the quasar's intense radiation passes through clouds of primordial gas on its long journey to us, atoms within that gas absorb very specific colors or wavelengths of light. Each element leaves a unique fingerprint, a dark line in the rainbow spectrum of the quasar's light. When we see these absorption lines shifted far into the red, we are not just measuring distance, we are conducting a forensic analysis of the early cosmos. We can detect the presence of hydrogen, helium, and the very first heavy elements forged in the hearts of the universe's earliest stars. This tells us what the building blocks of future galaxies were like and, crucially, what state that hydrogen was in. This leads us directly into one of the universe's greatest transitional periods, a time called the Epoch of Reionization. For hundreds of millions of years after the Big Bang, the cosmos was filled with a thick fog of neutral hydrogen gas. This fog was so dense it absorbed the ultraviolet light from the first stars and galaxies, trapping the universe in a featureless, dark haze. Then something happened to clear the fog. The leading theory is that the intense radiation from the first massive stars, and most importantly, from the first accreting supermassive black holes at the hearts of quasars, began to flood the cosmos. This powerful ultraviolet light had enough energy to strip electrons away from the neutral hydrogen atoms, a process called ionization. It was like a cosmic sunrise, slowly burning away the mist and making the universe transparent to light for the first time. The light from the most distant black holes acts as a probe sent directly through this era. By seeing how much of their light is absorbed by patches of remaining neutral hydrogen, we can map the progress of this great clearing. We can witness in real time across billions of years the moment the lights came on for the entire cosmos. These black holes are not just time machines, they are the very engines that may have powered the universe's transformation from an opaque void into the glittering, transparent expanse we see today. This brilliance solves a fundamental problem of cosmic observation. To see a black hole from the edge of the observable universe, you cannot rely on the black hole itself. By definition, a solitary black hole is a perfect void, an absence of light. So how do we detect these invisible titans billions of light years away? The answer lies in their behavior, in a state of cosmic violence so extreme it outshines entire galaxies. The most distant black holes we detect are almost never quiet. They are quasars. A quasar is not the black hole alone, but the entire phenomenal spectacle of a supermassive black hole in the act of feeding. At the heart of a young, gas-rich galaxy, vast rivers of matter spiral inward, drawn by the black hole's immense gravity. But this matter does not fall straight in. It forms a whirling, frenzied disk around the event horizon, known as an accretion disk. Imagine a drain at the center of a cosmic whirlpool, where the water is not liquid, but superheated gas and dust moving at nearly the speed of light. The friction and tidal forces within this disk are unimaginable. Particles collide with titanic energy, heating the disk to temperatures that can exceed trillions of degrees. This process converts the gravitational potential energy of the infalling matter into a torrent of radiation across the entire electromagnetic spectrum. A single, feeding supermassive black hole can therefore become the brightest persistent object in the cosmos. outshining the combined light of every single star in its host galaxy by a factor of 1,000 or more. It is this phenomenal luminosity, not the black hole's darkness, that acts as our beacon. A quasar is a lighthouse shining from the shores of the early universe, its piercing beam generated by the final, furious glow of matter just before it vanishes forever into the unknown. Without this catastrophic brilliance, the most distant black holes would remain forever hidden in the dark. This phenomenal feeding frenzy solves the problem of detection, but it creates an even deeper mystery. If these quasars are powered by supermassive black holes, their incredible brightness allows us to estimate the mass of the monster at their core. The numbers are staggering. We find black holes with masses of over 1 billion suns, shining from a time when the universe was less than 1 billion years old. This presents a monumental paradox. How does something that massive, that complex, assemble itself so quickly? According to our best models, a black hole grows by steadily consuming gas and stars. But there is a speed limit, a physical ceiling called the Eddington limit. This is the maximum rate at which matter can fall onto a black hole before the intense radiation it produces actually pushes the surrounding material away, cutting off its own food supply. It is like trying to fill a bucket under a torrential downpour, only for the splashback to keep most of the water out. Growing a billion solar mass black hole by standard, steady accretion would take far longer than the age of the universe at that point. It is simply not enough time, so the existence of these cosmic giants in the infant universe forces a profound question. Did they start from enormous seeds, perhaps the direct collapse of vast primordial gas clouds into 100,000 solar mass holes from the very beginning? Or did they find a way to break the rules, consuming matter in furious, chaotic bursts that exceeded the theoretical limits? This size paradox is not a minor detail. It is a fundamental challenge to our understanding of how structure forms in the cosmos, suggesting that the very first chapters of universal history were written in a language of violence and scale we are only beginning to comprehend. The paradox of their impossible size forces us to reconsider the very beginning of a black hole story. We must look for the seed, the initial speck of incredible density from which these billion solar mass giants could sprout in such a short cosmic time. The leading theories take us back to conditions even more extreme than the quasars themselves. One compelling idea is the direct collapse of primordial gas clouds. In the universe's first few 100 million years before many stars had formed, vast reservoirs of pristine hydrogen and helium could have gathered under gravity. But instead of fragmenting into many stars, these clouds may have collapsed in on themselves as a single, monstrous entity. With no heavy elements to help them cool and break apart, they would have fallen directly into a black hole with a starting mass of tens of thousands of suns. This is not a star that died, but a structure that skipped the star stage entirely, birthing a ready-made heavyweight seed perfectly positioned for rapid growth. Another candidate comes from the first generation of stars, known as population 3 stars. These were not like the stars of today. Forged from only hydrogen and helium, they are theorized to have been colossal, perhaps hundreds of times the mass of our Sun. Such behemoths live fast and die violently. After only a few million years, their cores would collapse in spectacular supernova or even direct collapse events, leaving behind black hole remnants of perhaps a few hundred solar masses. While smaller than direct collapse seeds, a whole cluster of these first star black holes could have merged together quickly, creating a larger core to begin the feeding frenzy. The most exotic theory pushes the origin back to the universe's very first moments. In the seething, dense conditions just after the Big Bang, random fluctuations in density could have been so intense that pockets of space-time directly pinched off into black holes. These primordial black holes would have nothing to do with stars or gas clouds. They would be fossils of the birth of space itself. They could range in size from a mountain to many solar masses, and if enough of the right size existed, they could have served as the ancient seeds around which the first galaxies coalesced. Each theory paints a different picture of the cosmic dawn, one of silent, direct collapse, one of the fiery death of the first stars, or one of quantum tremors frozen into reality. The truth may be a combination, a chaotic nursery where all these seeds were planted, waiting for the feast to begin. That brilliant accretion disk, the very engine of the quasar's power, gives off a very specific signature. It glows most intensely in ultraviolet light, a high-energy radiation just beyond the violet end of the visible spectrum. This is the primary fingerprint astronomers search for when hunting the most distant black holes. But here is the cosmic twist. By the time that ultraviolet light has traveled across 13 billion light-years of an expanding universe, it is no longer ultraviolet at all. The relentless stretching of space has transformed it. That energetic, short wavelength light gets stretched into longer, redder wavelengths. For the most ancient quasars, the ultraviolet glow from their searing hot disks arrives at our telescopes as infrared light. We are essentially seeing a cosmic color shift of unimaginable scale. This means our eyes, and even standard optical telescopes, are blind to these objects. To see them, we must use instruments designed to perceive the heat signature of the ancient universe. This is where specialized space observatories become our essential time-traveling eyes. Telescopes like the Spitzer Space Telescope and the Wide-Field Infrared Survey Explorer, known as WISE, were not looking at stars as we see them. They were scanning the heavens for faint whispers of infrared heat. Their digital eyes were tuned to the specific infrared wavelengths that correspond to the redshifted ultraviolet glow of primordial quasars. It is a bit like trying to identify a person by their voice, but after that voice has been slowed down to a deep, rumbling bass. You need the right kind of microphone to even hear it. WISE, in particular, conducted an all-sky survey, mapping the entire heavens in infrared light, creating a treasure map of potential ancient beacons. It would find thousands of bright infrared dots, and the very reddest, most promising of these would become targets for the most powerful ground-based telescopes. Those telescopes would then break the infrared light into a spectrum, looking for the specific chemical fingerprints that confirmed they were not just distant galaxies, but quasars powered by supermassive black holes. Every detection is therefore a two-step cosmic translation. First, the violent physics of an accretion disk shouts in ultraviolet. Then, the expanding universe stretches that shout into an infrared murmur. Finally, our technology listens carefully, translating that murmur back into a story of a monster from the dawn of time. While infrared light reveals the ancient glow of an accretion disk, it is another, more penetrating form of energy that confirms the true violence at the core. The Chandra X-ray Observatory, a space telescope designed to see the universe in X-rays, provides this critical evidence. X-rays are an extremely high-energy form of light, generated in the most ferocious environments imaginable. Around a supermassive black hole, the inner regions of the accretion disk and the base of powerful magnetic jets are heated to temperatures of millions of degrees. Matter there is not just hot, it is superheated and moving at relativistic speeds, and this chaos produces a torrent of X-rays. This is crucial because X-rays have a unique ability. They can punch right through thick clouds of gas and dust that would completely block visible or even infrared light. Many of these early galaxies are messy, chaotic places, filled with the debris of star formation that can shroud the central black hole. To optical telescopes, the core might be completely hidden, but Chandra sees straight through the cosmic fog. When it detects a powerful source of X-rays coming from the same location as a distant red infrared source, the case is closed. That X-ray signature is the smoking gun, the definitive proof that an active, feeding supermassive black hole is present. It is the signal from the very brink of the event horizon, a region of such intense gravity and heat that it warps the very fabric of space and time. Without Chandra's piercing vision, we might only see the outer glow of these distant quasars. With it, we witness the heart of the storm, confirming that these beacons of the early universe are powered by the most extreme engines in existence. That piercing X-ray vision reveals the black hole's presence, but its faint, ancient light often teeters on the very edge of detectability. To see further back, to the very first of these cosmic engines, we need a tool of unimaginable power. Nature itself provides one through a prediction of Einstein's theory of general relativity. Massive objects warp the fabric of space-time around them, and light traveling through this warped geometry does not follow a straight line. It bends when a massive object, like a galaxy cluster, lies directly between us and a far more distant object, like a primordial quasar. Something extraordinary happens. The cluster's immense gravity acts as a lens, bending and focusing the light from the background source. This phenomenon is called gravitational lensing. It does not just bend the light, it can magnify it, sometimes by a factor of 10, 50, or even 100. Think of it as a natural cosmic telescope sculpted by gravity itself. A distant quasar whose light would normally be an indecipherable speck in our detectors can be stretched and amplified into a discernible arc or multiple bright images around the foreground cluster. This amplification is our only chance to see the very earliest and therefore faintest supermassive black holes in the universe. Without this natural assist, their light would be lost in the noise. Astronomers actively search for these rare, perfect alignments, knowing that when they find one, the foreground galaxy cluster becomes more than just an object of study. It becomes a lens, a tool that peers deeper into the cosmic past than any human-built telescope ever could. It turns the universe's own architecture into a window, allowing us to witness the ignition of the first monsters in stunning, magnified detail. Gravitational lensing offers a precious glimpse, but it underscores a fundamental truth about the cosmic frontier. These most distant black holes are astonishingly rare. For every one we manage to detect, there are untold billions of ordinary galaxies from the same era that do not host such brilliant feeding monsters. Finding them is not a simple matter of pointing a telescope at the sky. It is a painstaking cosmic treasure hunt across unimaginable volumes of empty space. Consider the scale of the search. To find a quasar from the universe's first billion years, astronomers must survey enormous swaths of the heavens. Projects like the Sloan Digital Sky Survey have mapped millions of galaxies, but that is just a fraction of what is out there. Within these vast surveys, researchers then filter for the telltale signs. Objects that are extremely bright in infrared light but virtually invisible in optical light, indicating a massive redshift. Even then, a bright infrared dot could be many things a nearby dusty galaxy, a cool star within our own Milky Way, or a technical glitch in the data. Each candidate must be followed up with hours of observation on the world's most powerful telescopes, like the Keck Observatory or the Very Large Telescope, to obtain a detailed spectrum. That spectrum is the final verdict. It must show the specific, redshifted fingerprints of elements like carbon or magnesium, stretched exactly as predicted for that immense distance. Out of millions of surveyed objects, only a handful survive this rigorous vetting to be confirmed as quasars from the cosmic dawn. The technological leap required is immense. We are not just building bigger mirrors, we are creating more sensitive infrared detectors and writing sophisticated algorithms to sift through petabytes of data, searching for that one in a billion needle in the cosmic haystack. Their rarity makes each confirmed detection a priceless data point, a singular beacon illuminating a dark and distant chapter of history we are only beginning to read. That brilliant beacon, however, creates a profound observational dilemma. The very light that allows us to see the black hole from across the universe also blinds us to its home. A quasar's core can outshine its entire host galaxy by a factor of 1,000, drowning the faint, sprawling starlight in a sea of glare. It is like trying to study the delicate structure of a street lamp's glass while staring directly into its 100-watt bulb. The host galaxy is the crucial context, the nurturing environment where this cosmic monster formed and grew. We need to see it to understand the conditions that gave rise to such a behemoth so quickly. Was it a massive, chaotic galaxy, rich with gas and prone to violent mergers? Or was it surprisingly ordinary, suggesting the black hole grew with freakish efficiency? The quasar's own brilliance hides the answers. To solve this, astronomers must become cosmic detectives, using clever techniques to block out the central glare. One method involves sophisticated computer modeling. They create a precise digital model of the quasar's point-like, brilliant core based on its known properties. Then, like digitally subtracting a blinding light from a photograph, they carefully remove that modeled glare from the actual telescope image. What remains, if they are lucky and the observation is exquisitely sharp, is the faint, fuzzy glow of the underlying galaxy, a ghostly halo of ancient stars revealed from behind the spotlight. Another technique leverages the unique capabilities of space telescopes like Hubble and the James Webb Space Telescope. By using special filters and coronagraphs, instruments designed to block the light of bright stars, they can physically mask the quasar's core. This is akin to using your hand to shield your eyes from the sun to see the landscape around it. With the central engine artificially dimmed, the faint, extended light of the host galaxy can slowly emerge from the darkness. These painstaking efforts have shown that many of these early quasars reside in surprisingly compact, yet incredibly dynamic galaxies. They are often seen merging with neighbors, a cosmic collision that funnels vast reservoirs of gas directly toward the central black hole, feeding its brilliance and explaining its rapid growth. Seeing the host is more than an academic exercise. It is the difference between studying a lone predator and understanding the entire ecosystem that created it. This blinding brilliance is not just an observational challenge, it is a transformative force. The radiation flooding from these ancient quasars does more than light up the cosmos, it actively sculpts it. The same energy that makes them visible across the universe has a profound and paradoxical effect on their own homes. These supermassive black holes can become engines of galactic sterilization. The process begins with the quasar's intense ultraviolet and X-ray radiation, which pours out in all directions. This high-energy flood does not just pass through the surrounding gas of the host galaxy, it slams into it. The radiation heats the vast clouds of molecular hydrogen, the very raw material from which new stars are born. Imagine a gentle mist that could freeze into beautiful snowflakes. Now imagine blasting that mist with a roaring blowtorch. The mist doesn't just get warm, it gets scattered and ionized, its delicate structure destroyed. That is what the quasar's radiation does to stellar nurseries. It heats the galactic gas to such extreme temperatures that the gas atoms move too fast and with too much energy to collapse under their own gravity. The critical, delicate process of star formation grinds to a halt. This is called quenching. The black hole, by feasting so violently, can starve its own galaxy of future generations of stars. It effectively puts the brakes on the galaxy's growth, potentially turning a vibrant, star-forming spiral into a quiet, aging elliptical galaxy far sooner than normal. This establishes a powerful feedback loop, a cosmic self-regulation where the monster's appetite determines the fate of its entire domain. That feedback loop of creation and destruction is governed by a single, fundamental property, the black hole's mass. To understand its power, we must first know its weight. But how do you weigh a monster you cannot see from 13 billion light-years away? You do not use a scale. You listen to the frantic dance of light around it. The method is as ingenious as it is indirect, relying on the quasar's own brilliant emission. Within the torrent of light from the accretion disk, specific chemical elements leave their fingerprints. Atoms like magnesium and carbon, superheated in the swirling maelstrom, emit light at very precise wavelengths. We see these as bright lines in the quasar's rainbow spectrum, known as emission lines. But these lines are not perfectly sharp. They are broad, smeared out into a wide band of color. This broadening is the key. The gas emitting this light is not sitting still. It is whirling around the black hole at incredible speeds, caught in a gravitational grip of unimaginable force. Some of this gas is moving toward us and some is moving away. Due to the Doppler effect, the same principle that makes a siren's pitch change as it passes, light from gas moving toward us is shifted slightly toward the blue end of the spectrum. Light from gas moving away is shifted toward the red. The result is that the sharp emission line gets stretched and smeared into a broad hump. The width of that hump tells a direct story. The faster the gas is orbiting, the broader the emission line becomes, and the speed of that orbiting gas is dictated by one thing alone: the mass of the central black hole. It is a simple, elegant equation from the laws of gravity. A more massive black hole exerts a stronger gravitational pull, forcing nearby gas to orbit at much higher speeds to avoid falling in. So, by carefully measuring the width of, say, the magnesium emission line in the spectrum of a distant quasar, astronomers can calculate the orbital velocity of the gas. Plug that velocity and an estimate of the gas's distance from the center into Newton's and Kepler's laws, and out pops a number: the mass of the invisible Titan. It is a cosmic autopsy performed with light, using the frantic motion of doomed matter to weigh the silent heart of darkness that commands it. This weight, once measured, reveals a startling cosmic imbalance. In our local, modern universe, astronomers have discovered a remarkably tight relationship between a supermassive black hole and its home. The mass of the central black hole is typically about 1/500th of the mass of the galaxy's central bulge of stars. It is a consistent ratio, a rule that seems to govern galactic architecture across billions of years. But when we look at the most distant quasars, that rule shatters. The black holes from the cosmic dawn appear to be surprisingly, almost impossibly overweight. Their masses, derived from those broad emission lines, are often far too large for the size of their host galaxies, which we painstakingly uncover by blocking out the quasar's glare. Imagine a newborn baby with the muscle mass of a heavyweight boxer. The proportions are all wrong. A black hole that should be a modest fraction of its galaxy's bulk instead rivals or even surpasses it in gravitational influence. This suggests a fundamental shift in how galaxies grew in the infant universe. Perhaps the black hole formed first, a massive seed that acted as a gravitational anchor, pulling in the gas that would later form the galaxy around it. Or the galaxy and its black hole grew together, but in a frantic, chaotic race where the black hole sprinted ahead, feasting on a dense, rich supply of gas before the galaxy's stars had a chance to form in significant numbers. This broken correlation is a vital clue. It tells us that the early cosmos operated under different rules, a period of rapid, violent assembly where the monsters could grow to full size before their homes were even finished being built. This cosmic imbalance, this broken rule of galactic proportions, demands a new kind of eye. We have pushed our current telescopes to their absolute limits, squinting at the faintest whispers of infrared light to weigh these ancient monsters and glimpse their homes. To go further, to truly understand the birth of the first black holes, we needed a revolutionary instrument, one designed from the ground up to see the dawn of time. That instrument is now open, and its name is the James Webb Space Telescope. Webb is not merely an upgrade, it is a paradigm shift in our quest to see the cosmic dawn. Its entire design is optimized for one primary mission: to see the universe in infrared light with a sensitivity and resolution that is simply unprecedented. Remember, the ultraviolet glow from those first quasars is stretched by cosmic expansion into the infrared by the time it reaches us. Webb's massive 6.5-meter gold-coated mirror acts as a colossal light bucket, specifically tuned to gather these faint, long-wavelength photons. Where Hubble gave us stunning visible light images of the modern universe, Webb is built to see the heat signature of creation itself. Its position is also critical. Orbiting at a stable point nearly 1 million miles from Earth, far beyond the interference of our planet's heat and light, its instruments are kept incredibly cold. This coldness is essential because to detect the faint infrared warmth of distant galaxies, the telescope itself must not radiate any heat of its own that would drown out the signal. It is like trying to hear a pin drop in a silent room versus hearing it in a roaring factory. Webb provides that perfect, silent, cold vacuum of space as its listening post. With this unparalleled vision, Webb is poised to find quasars so distant and so faint they have been completely invisible until now. It will not just find more of them, it will study them in breathtaking detail, finally allowing us to see the host galaxies of these early monsters clearly without the blinding glare. We will witness the gas and dust swirling around them, measure the rates of star formation they are quenching, and perhaps even catch them in the act of merging, the very events that fueled their impossible growth. Webb is our ultimate time machine, and it is now pointing its golden eye toward the edge of time, ready to rewrite the first chapter of cosmic history. The quest to find these earliest engines brings us to a pivotal moment in cosmic history, a time so foundational it has earned a name of its own, the Cosmic Dawn. This is not a single event, but a transformative era spanning the universe's first few 100 million years. It marks the end of the Dark Ages, that silent, featureless epoch when the cosmos was a vast, cooling sea of hydrogen and helium gas. The Cosmic Dawn was the moment the lights began to flicker on. Within the densest knots of that primordial gas, the very first stars ignited. These were not like the stars of today. They were colossal, short-lived behemoths, and their brilliant, harsh ultraviolet radiation began to pierce the universal fog. Soon after, gravity pulled collections of these stars and gas together, forming the very first fragile galaxies. It is within these infant galaxies that the first supermassive black holes must have taken root. Finding a black hole from this specific era is the ultimate goal, the final frontier in our journey back in time. It would mean pushing our observations to within a mere 200 or 300 million years of the Big Bang itself. At that distance, the redshift value would soar above 10, perhaps even approaching 20. The light from such an object would be stretched so profoundly that it would arrive not just as infrared, but as far infrared or even submillimeter waves, the faintest whisper of heat from the beginning of everything. The challenge is monumental because the Cosmic Dawn is also the era of first light, meaning the background fog of the universe was only partially cleared. Detecting a single quasar from this time is like trying to spot a specific lighthouse through a thick, receding mist, while standing on a shore 13 billion light-years away. Yet, this is precisely what the James Webb Space Telescope was built to do. Its mission is to peer directly into this dawn, to search for the faint infrared signatures of black holes that were present when the first galaxies were just assembling. Discovering one would be more than a record breaker. It would be a direct glimpse at the seed from which all later cosmic structure grew, showing us the exact conditions under which the universe's most powerful engines were first switched on. The universe's greatest mystery may be hiding in plain sight within the fury of those ancient quasars. Dark matter, the invisible, unidentified substance that makes up over 85% of all matter in the cosmos, exerts a gravitational pull that binds galaxies together. Yet for all its influence, we have never directly observed a single particle of it. Its nature remains the most profound puzzle in physics. Now, a bold and speculative idea suggests the key to this mystery might lie in the very objects we have been discussing. The most distant black holes in their youth could have acted as dark matter factories. The theory hinges on the unimaginable conditions present in the early universe, particularly within and around these first supermassive black holes. In those dense, energetic environments, particles would have collided with energies far exceeding anything we can create in our most powerful particle accelerators. Some physicists propose that certain hypothetical dark matter particles, like weakly interacting massive particles or WIMP, could have been forged in these collisions. Think of the accretion disk not just as a source of light, but as a cosmic crucible, a particle smasher of astronomical scale. Within its churning plasma, exotic reactions could have produced stable, massive particles that simply do not interact with light, the perfect candidate for dark matter. Even more intriguing is the possibility of annihilation. Some dark matter theories suggest that when a particle of dark matter meets its antimatter counterpart, they annihilate each other in a burst of energy. The dense halos of dark matter that are thought to surround all galaxies, including these ancient ones, would be funneled and concentrated by the black hole's immense gravity. This could create a hotspot where annihilation events are frequent, releasing a subtle but potentially detectable signature in the form of gamma rays or other exotic radiation. While we have no definitive proof, this idea creates a breathtaking cosmic link. The most brilliant, distant beacons from the dawn of time might not only have cleared the cosmic fog and shaped the first galaxies, they could also have been the birthplaces of the very shadow that holds the modern universe together. The spin of a black hole is a permanent record of its violent past. While we cannot see the event horizon itself, we can infer this rotation from the behavior of matter just outside it in the inner accretion disk. For the most distant quasars, astronomers have begun to measure this spin, and the results are startling. Some of these ancient monsters appear to be rotating at nearly the maximum speed allowed by the laws of physics. This is a profound clue to how they grew so massive so quickly. A black hole gains spin or angular momentum from the material it consumes. If that material falls in from random directions, like during chaotic galaxy mergers where gas clouds collide from all sides, the different spins would cancel each other out, resulting in a slower overall rotation. But if the material flows in a steady, organized stream from a single direction, like a sustained river feeding into a whirlpool, each new parcel of matter adds its momentum in the same direction. This spins the black hole up faster and faster over time. The detection of near maximum spin in some early supermassive black holes suggests a surprisingly orderly growth story. It implies these giants were fed by a prolonged, stable, and incredibly rich diet of gas, likely funneled by a vast, smooth disk in their host galaxy over hundreds of millions of years. This was not a series of violent, random collisions, but a continuous, gluttonous feast. The monster did not grow by stumbling from one chaotic meal to the next. It sat at the center of a cosmic conveyor belt, spinning up to ferocious speeds as it consumed the heart of its galaxy with a terrifying, singular focus. That ferocious spin does more than just record a history of gluttony. It can power one of the most spectacular and destructive phenomena in the universe. Some of these ancient quasars do not just shine with a brilliant disk, they also fire twin lances of pure energy directly into the cosmos. These are relativistic jets, beams of charged particles accelerated to over 99% the speed of light, screaming away from the black hole's poles. The physics behind them is as elegant as it is violent. Not all the matter spiraling toward the event horizon gets consumed. A fraction of it, caught in the black hole's immensely powerful magnetic field lines, gets channeled and focused along the rotational axis, the black hole's north and south poles. There, it is catapulted outward in a tightly collimated beam, a cosmic blowtorch of protons and electrons moving with so much energy they literally punch through their own galaxy. The scale is incomprehensible. While the host galaxy of an early quasar might be 50,000 light-years across, these jets can stretch for hundreds of thousands, even millions of light-years. They extend far beyond the realm of stars, reaching out into the desolate voids between galaxies. This means a single black hole, a pinprick at the heart of one galaxy, can project its influence across intergalactic space, a dominance that defies all sense of proportion. The jet is not a gentle stream, it is a tsunami of energy. Where it plows into the sparse gas of the intergalactic medium, it creates colossal shock waves, heating the material to millions of degrees and preventing it from ever cooling down to form new stars in neighboring galaxies. These jets are the ultimate feedback mechanism on a cosmic scale. They regulate not just their own galaxy's growth, but the growth of entire future clusters of galaxies, carving vast cavities in the intergalactic gas and depositing energy across millions of light years. They are the universe's most powerful construction tools and its most effective wrecking balls wielded by monsters from the dawn of time. These jets, carving their paths through intergalactic space, are just one expression of a far more pervasive influence. The raw, unshielded radiation pouring from a young quasar does not travel in a neat beam. It floods out in all directions, a spherical shockwave of energy that reshapes the very fabric of the cosmos on the largest scales. This brings us to one of their most profound and universal roles. The most distant black holes were likely instrumental in ending the universe's dark ages, serving as primary engines for the epoch of reionization. Remember, for hundreds of millions of years after the Big Bang, the cosmos was filled with a dense fog of neutral hydrogen gas. This fog absorbed ultraviolet light, keeping the universe opaque. For the cosmos to become clear, that fog had to be burned away. The first stars certainly helped, but their light was often trapped within their own dense, dusty galaxies. Quasars were different. Their ultraviolet radiation was millions of times more powerful, and it emanated from a single, brilliant point capable of punching out of its host galaxy and into the vast intergalactic voids. This radiation had a very specific effect on the surrounding hydrogen. Each ultraviolet photon carried enough energy to violently strip an electron away from a hydrogen atom, a process called ionization. Think of it like a cosmic sandblaster. The relentless torrent of high-energy light from thousands of these early quasars slowly, over hundreds of millions of years, scoured the neutrality from the hydrogen fog. It transformed the universe from a murky soup of neutral atoms into a transparent sea of charged particles, allowing light to travel freely across billions of light years for the first time. We are, in a very literal sense, seeing the universe today because those ancient monsters helped clear the air. The light from the most distant quasars itself acts as the proof. As their light journeys to us, it passes through whatever patches of neutral hydrogen remain along the way. By analyzing how much of specific wavelengths are absorbed, astronomers can map the progress of this great clearing. The evidence suggests reionization was a patchy, uneven process, like watching fog burn off a landscape. Some areas clear first, while others remain shrouded. The brilliant beacons of the first quasars were likely the torches that lit the way, their fierce glow defining the moment the cosmic dawn gave way to a transparent, star-filled day. The brilliant glare of quasars tells only one part of the story. For every supermassive titan shining from the cosmic dawn, there should be countless smaller, quieter shadows. These would be the stellar mass black holes, the remnants of the very first generation of stars. When those colossal population 3 stars, hundreds of times the mass of our Sun, burned through their fuel in just a few million years, their cores would have collapsed. Many would have ended not in supernova, but in direct collapse, leaving behind black holes perhaps 50 or 100 times the mass of our Sun. These are the true pioneers, the first generation of dark remnants scattered throughout the infant cosmos. Yet, we have never seen one from that era. The challenge is one of sheer scale and silence. A solitary stellar mass black hole, unless it is actively feeding from a companion star, emits nothing. It is a perfect void against an already dark backdrop. Even if one were actively feeding, its glow would be a faint candle compared to the stadium lights of a quasar, completely drowned out across 13 billion light years. Detecting these faint whispers requires a different kind of listening. One promising method looks for transient events, sudden flashes of energy that might betray their presence. For instance, if one of these ancient stellar black holes were to tear apart and consume a passing star, the resulting tidal disruption event would create a brief, bright flare of light. In the modern universe, we see these flares in nearby galaxies. Spotting such a flash from the edge of time, however, would be like trying to see a single camera flash on a distant mountain during a lightning storm. It requires constant, vigilant monitoring of vast patches of sky, hoping to catch that one fleeting moment of violence. Future observatories, with their wider fields of view and rapid alert systems, may finally give us a census of these smaller shadows, completing our picture of the first dark population in the universe. The brilliant glare of a quasar is not a single color, but a cascade of energy born from unimaginable heat. At the source, within the heart of the maelstrom, the accretion disk glows with a ferocious blue-white intensity. This is the true color of a distant quasar, a fact that seems at odds with their designation as extremely red objects. The reason lies in the physics of temperature. Just as a heated piece of metal glows red, then orange, then white as it gets hotter, the temperature of an accretion disk dictates its primary color. The disks around these supermassive black holes are not merely hot, they are infernos, reaching temperatures of hundreds of thousands of degrees. At such extremes, they emit most of their light not in the red part of the spectrum, but in the high-energy blue and ultraviolet range. This is their rest frame color, the hue they would appear to have if you could somehow view them up close without the distorting effect of cosmic expansion. So, if the engine itself is blazing blue, why do our telescopes see it as a faint red dot? The answer is the relentless stretch of the expanding universe. That pristine, brilliant blue and ultraviolet light embarks on a journey of over 13 billion years. As space itself expands during that eon-long voyage, the wavelengths of that light are stretched along with it. Blue light has a short wavelength, stretch it, and it becomes longer, moving toward the red and then infrared part of the spectrum. It is the ultimate cosmic color shift. The more distant the quasar, the longer the journey, and the more extreme the stretching. For a quasar at the edge of the observable universe, its original blue glow is stretched so dramatically that by the time it reaches Earth, it has been transformed entirely into infrared radiation, invisible to our eyes but detectable as heat by our specialized instruments. We are, in effect, seeing a ghost of its true color, a brilliant blue scream from the dawn of time that has been slowed to a deep infrared whisper. That brilliant, stretched whisper carries more than just the story of the black hole itself. It carries a detailed map of every cloud and wisp of matter it has passed through on its 13 billion-year journey to our telescopes. This makes the most distant quasars the ultimate cosmic lighthouses. Their intense, pinpoint beams of light shine through the vast, empty spaces between galaxies, illuminating the faint, diffuse material that would otherwise be completely invisible. This material is the intergalactic medium, the sparse gas that fills the cosmic web. It is not a perfect vacuum, but a tenuous fog of mostly hydrogen and helium, with traces of heavier elements scattered by ancient supernova. Studying it directly is nearly impossible because it emits almost no light of its own. But when you place a brilliant, distant quasar behind it, everything changes. As the quasar's light travels toward us, it passes through these invisible clouds. Atoms within the clouds absorb very specific wavelengths of that light, depending on their chemical composition. Hydrogen, for example, absorbs a particular shade of ultraviolet light. By the time that light reaches us, stretched into the visible or infrared, those absorbed wavelengths show up as dark lines in the quasar's rainbow spectrum. Each dark line is like a fingerprint telling us not only what element is present in a cloud, but also, thanks to the redshift, exactly how far away that cloud is. It is a forensic technique on a cosmic scale, Astronomers call this the Lyman alpha forest. In the spectrum of a high redshift quasar, they do not see just one dark line from hydrogen, but a dense thicket of them. Each line represents a different cloud of neutral hydrogen at a different distance along the line of sight, each at a slightly different redshift. The pattern of these lines is breathtakingly complex. Dense clusters of lines reveal where the cosmic web is thick with gas, perhaps at the intersections of filaments where galaxies are forming. Sparse gaps show the vast, empty voids. By analyzing this forest, scientists can reconstruct the three-dimensional distribution of matter across billions of light years, using a single beam of ancient light as their probe. They can measure the temperature and density of the gas, track how it was enriched with elements like carbon and oxygen over time, and even feel the subtle tug of dark matter, which influences how these clouds are distributed. The quasar itself is the spotlight, but the shadows it casts, those thousands of delicate dark lines in its spectrum, paint the true portrait of the universe's invisible architecture. That forest of spectral lines is a beautiful map, but its clarity depends entirely on the purity of the beacon that created it. The light from a potential distant quasar must be pristine, uncontaminated by anything closer to us in the cosmic timeline. This leads to one of the most painstaking challenges in the entire hunt, the problem of contamination. When a telescope like WISE scans the sky and flags an object as extremely bright in infrared but dark in visible light, the initial excitement is palpable. It could be a quasar from the cosmic dawn, but it could also be something far more mundane, a cosmic imposter wearing a clever disguise. The primary suspects are much closer to home. One is a cool, faint star within our own Milky Way, a red dwarf or brown dwarf. These objects are intrinsically dim and red, and if one lies along our line of sight, its infrared signature can look remarkably similar to the redshifted glow of a distant quasar. The other major imposter is a dusty, star-forming galaxy from a more recent cosmic era. These galaxies are filled with vast clouds of dust that absorb visible starlight and re-radiate it as infrared heat. From our vantage point, such a galaxy can appear as a bright infrared dot with little visible light, mimicking the key signature of an ancient quasar. Telling these apart with a simple photograph is impossible. The only tool that can deliver a verdict is a detailed spectrum. This requires follow-up observations on the world's most powerful ground-based telescopes, like Keck or the Very Large Telescope. Astronomers must secure precious hours of observation time, point the massive mirror at that single, faint dot of light, and split its glow into a rainbow spectrum. They are looking for the definitive fingerprints, the broad, smeared emission lines from fast-moving gas around a supermassive black hole, stretched exactly to the redshift predicted by the object's color. If they see the unmistakable signature of, say, magnesium or carbon, shifted far into the infrared, the discovery is confirmed. If the spectrum shows only the bland, narrow features of a cool star or the messy dust signature of a nearby galaxy, the candidate is dismissed. It is a rigorous process of elimination, where the universe's most ancient beacons are identified by patiently ruling out every other possibility, one spectral line at a time. The light from these quasars illuminates more than just their host galaxies. It reveals the crowded neighborhoods they were born into. Some of the most distant quasars are not solitary giants in the void. They are the blazing centers of immense cosmic metropolises in their earliest stages of construction. Astronomers call these regions protoclusters, and they are the embryonic forms of the most massive galaxy clusters we see in the universe today. A modern galaxy cluster can contain thousands of galaxies, all bound together by gravity in a volume of space tens of millions of light years across. A protocluster is that same region, seen not in its mature glory, but as a sprawling, chaotic construction site when the universe was less than 1/10 of its current age. Within this dense knot of dark matter and primordial gas, galaxies are forming at a frantic pace, colliding and merging, their gas funneling into central hubs. And at the very heart of the densest peak, where the gravitational well is deepest, sits the supermassive black hole that will become the cluster's brightest quasar. This is a profound clue to their origin. The most massive black holes did not form at random locations. They grew in the richest environments, the densest peaks of the early cosmic web where the flow of raw material was most abundant. Think of it like cities on Earth. The largest metropolises did not spring up in the middle of deserts or oceans by chance. They grew where resources were plentiful along major rivers, at natural harbors, at the crossroads of trade routes. In the infant universe, the equivalent resource is gravity itself. The densest knots of dark matter pulled in the most gas, which fueled both rapid star formation and, at the very center, the voracious growth of a supermassive black hole. The quasar becomes the brilliant street lamp marking the future downtown of a cosmic city that will take billions more years to fully assemble. Finding a quasar within a protocluster confirms a fundamental prediction of how structure formed in our universe. The greatest monsters arose in the deepest gravitational pits, feasting on the cosmic bounty that flowed there first. But even the deepest gravitational wells have a limit to how fast they can be drained. There is a fundamental law of physics that governs how quickly a black hole can eat, a rule known as the Eddington limit. Picture a star not as a static ball of fire, but as a constant, delicate battle. In its core, nuclear fusion creates an outward pressure, a radiant force that pushes against the star's own immense gravity, trying to crush it inward. For most of a star's life, these two forces are in perfect, stable balance. A similar equilibrium exists around a feeding black hole. As matter falls in and heats up, it produces radiation light, X-rays, and ultraviolet photons. This radiation exerts an outward pressure on the very gas that is trying to fall inward. The Eddington limit is the precise point where these two opposing forces balance. It is the maximum luminosity, the maximum brightness, a black hole can achieve from steady accretion before the radiation it produces becomes so intense that it literally blows away its own food supply. It is the cosmic equivalent of a furnace burning so hot it blows out its own fuel. This limit is not arbitrary, it is calculated directly from the black hole's mass. A more massive black hole has a stronger gravitational grip, so it can hold onto gas against a fiercer radiative push. Therefore, its Eddington limit is higher. For a billion solar mass black hole, this maximum stable brightness is almost unimaginable, outshining a galaxy by thousands of times. Yet this very law creates our central paradox. Growing such a monster by steady, Eddington-limited accretion from a small seed would take far longer than the age of the early universe allowed. So, how did they do it? The answer may lie in breaking the rules. Astronomers are finding tantalizing hints that some of these ancient quasars were not polite, steady diners. They were cosmic gluttons, consuming matter in violent, messy bursts that temporarily exceeded the Eddington limit. This is called super-Eddington accretion. Imagine trying to fill a bucket in a hurricane. The downpour is so intense that water splashes violently over the sides. More is flying out than going in, but for brief, chaotic moments, an enormous volume still manages to pour into the container. In a super-Eddington state, the black hole's gravity is so overwhelming, and the inflow of gas is so dense and chaotic, that matter can be forced inward faster than the radiation can push it back out. The accretion disk becomes puffed up, thick and turbulent, with some material being blown away in powerful winds while other streams slam directly into the event horizon. This is not a stable state. It is a frenzy, a feast or famine pattern that cannot last for long cosmically, perhaps only thousands or millions of years. But during these brief, spectacular binges, a black hole can gain mass at a phenomenal rate, potentially solving the puzzle of their rapid growth. The evidence for this comes from the very spectra of these distant quasars. Some show signs of incredibly thick, fast outflows, the telltale winds of material being violently ejected by the extreme radiation pressure, a signature of a system pushing past its limits. These ancient monsters may have grown not by steady meals, but by occasional catastrophic banquets, gorging themselves in defiance of the universe's own speed limits. These violent winds, the byproduct of a feeding frenzy, do more than just regulate the black hole's own meal. They act as cosmic sculptors on a truly grand scale. The most powerful quasar outflows can carve enormous spherical cavities in the surrounding intergalactic gas, like a blowtorch held steady in a dense fog. Imagine the scene. At the center of a young galaxy, the supermassive black hole erupts. Along with its brilliant radiation, it launches a hurricane of charged particles and superheated gas, not just in narrow jets, but in a more spherical, explosive wind. This wind expands outward in all directions, a supersonic shockwave plowing into the delicate, sparse hydrogen that fills the space between galaxies. The force is immense. The wind slams into the intergalactic gas, sweeping it up and pushing it ahead like a cosmic snowplow. The gas at the leading edge gets compressed into a dense, hot shell, while the interior of this expanding sphere is evacuated, creating a vast, empty bubble. These are not small structures. A single quasar bubble can be hundreds of thousands of light years across, large enough to contain multiple galaxies within its hollow interior. Their impact is profound and lasting. Inside the bubble, the conditions for galaxy formation are fundamentally altered. The raw material for making new stars, that cool, dense hydrogen gas, has been violently cleared out. Any infant galaxies forming inside this cavity find themselves in a cosmic desert, starved of the fuel they need to grow. Their star formation is effectively quenched, not by radiation this time, but by a simple lack of building blocks. Meanwhile, the swept-up gas at the bubble's edge becomes the site of a different story. As this colossal shell of material expands and eventually cools, its immense gravity can trigger the collapse of new pockets within it. It seeds the next generation of galaxy formation, but now in a neat spherical ring around the void. The quasar, in a final act of feedback, has not just destroyed a nursery, it has drawn a blueprint for a new one. It has reshaped the cosmic landscape for eons, ensuring that future structures will form not at random, but along the precise, bubble-like frontier it created billions of years earlier. Such a colossal bubble of influence suggests a single, dominant power, but the early universe was a place of chaotic collisions. This leads us to a fascinating frontier, the search for binary, supermassive black holes from the cosmic dawn. We have good reason to suspect they existed. In that crowded, violent era, young galaxies were constantly smashing together, merging to build larger structures. If each of those colliding galaxies hosted its own central supermassive black hole, the result of the merger would be two titans trapped in a gravitational dance at the heart of a single, chaotic galaxy. They would spiral inward over millions of years, orbiting one another in a tightening cosmic waltz before finally coalescing into an even larger monster. Finding such a pair from 13 billion years ago would be a monumental discovery, a direct snapshot of the building process in action, but detecting them is a staggering challenge. At such distances, the two black holes would appear as a single, blurry point of light even to our most powerful telescopes. We cannot simply take a picture to see them separately. Instead, astronomers must become detectives of light, looking for subtle, telltale signatures in the quasar's behavior. One promising clue is periodic brightness. If two supermassive black holes are orbiting each other closely, their gravitational tug can disrupt the flow of gas in their shared accretion disk in a regular, rhythmic pattern. This could cause the quasar's overall brightness to pulse, to dim and brighten on a predictable schedule that matches the orbital period of the binary pair. It would be like watching a lighthouse with two rotating beams that occasionally block each other, creating a rhythmic flicker in its signal across the cosmos. Another, even more profound signature would be in the fabric of space-time itself. As two supermassive black holes spiral closer and closer, they churn the very geometry of the universe around them, sending out ripples known as gravitational waves. These are not waves of light or matter, but literal stretches and squeezes in the distance between objects. The merger of 2 billion solar mass black holes would be the most energetic event since the Big Bang, generating a deafening blast of gravitational wave energy. While our current ground-based detectors like LIGO are tuned to hear the higher-pitched chirps of merging stellar mass black holes, the merger of supermassive giants produces a much deeper, lower-frequency rumble. To hear this ancient chorus, we need a different kind of observatory. Future space-based missions like the planned Laser Interferometer Space Antenna, or LISA, will consist of 3 spacecraft flying in a giant triangle, millions of miles apart, using lasers to measure microscopic changes in distance caused by passing gravitational waves. LISA will be sensitive to the low-frequency waves produced by these colossal, early universe mergers. It could, in theory, detect the final moments of a binary black hole merger that occurred when the universe was only a few 100 million years old. The signal would be a slow, building siren song over years, culminating in a final, definitive snap as the two event horizons become one. Finding such a binary, either by its flickering light or its space-time ripples, would do more than break a record. It would show us the violent mechanism behind the growth of the first cosmic giants, proving that the path to becoming a monster was often a partnership that ended in a catastrophic embrace. That final, catastrophic embrace would send tremors through the very geometry of space. But long before two black holes merge, their immense gravity, and the gravity of all the matter in the cosmos, performs a more subtle, continuous magic on the light traveling toward us. The path of a photon from a 13-billion-year-old quasar is not a straight line. It is a winding journey through a universe whose fabric is warped and dimpled by every galaxy, every cluster, and every strand of dark matter it passes. We have seen how a massive galaxy cluster can act as a powerful lens, dramatically magnifying a distant quasar's image. Yet there is a far more pervasive, delicate version of this effect at work across the entire sky, an invisible hand that gently sculpts the light from the edge of time. This is weak gravitational lensing. Unlike the strong lensing that creates brilliant arcs and multiple images, weak lensing does not dramatically distort. Instead, it imparts a faint, coherent stretch to the shapes of billions of distant background objects, including the faint, smeared glow of the most ancient quasars and their host galaxies. Imagine looking up at the night sky through a vast, imperfect pane of glass, one with subtle, wavy variations in thickness. The stars behind it would not appear broken or multiplied, but their positions would be minutely shifted, their circular shapes ever so slightly stretched into tiny ellipses. The universe itself is that imperfect pane. The cumulative gravity of all the unseen dark matter and the diffuse cosmic web acts as a complex lens, warping the trajectories of light rays in a predictable, though incredibly faint way. For a single, distant quasar, this effect is too small to measure. Its point of light might be shifted by a fraction of a pixel in our deepest images. But by studying the subtle statistical distortions across thousands of these ancient beacons, astronomers can perform an extraordinary feat. They can map the invisible. They can trace the distribution of all the matter, both light and dark, that lies between us and the cosmic dawn. Each distorted quasar image is a single data point. Collect enough of them and a ghostly picture emerges, the three-dimensional skeleton of the universe, revealed not by the light it emits, but by the way it bends the light from sources far beyond. This means the faint, stretched light from the most distant black holes does more than tell their own story. It carries an imprint of every gravitational hill and valley it traversed, allowing us to chart the cosmos's hidden architecture with the oldest beacons as our guide. This impossible wait from the dawn of time is more than a puzzle, it is a ticking clock. The existence of billion solar mass black holes a mere 700 million years after the Big Bang forces us to place the entire early universe on a strict, unforgiving schedule. Think of it like a detective arriving at the scene of a crime and finding a fully grown oak tree in the middle of a room that was sealed just a year earlier. Its mere presence tells you something profound about the conditions inside that room long before it was sealed. These ancient black holes are our cosmic oak trees. Their mass and age set a hard deadline for the universe's first chapters. Every model we have for how the cosmos evolved, how dark matter clumped, how gas cooled, how the first stars ignited must now pass a brutal test. Can it build a monster of that size in that specific window of time? If a theory of dark matter, for instance, predicts that structures form too slowly, it is immediately ruled out by the glaring evidence of these early giants. They act as cosmic chronometers, their immense gravity serving as the hands on a clock that started ticking at the moment of creation itself. Their existence tells us that the seeds for cosmic structure must have been planted incredibly early, perhaps in the first fractions of a second after the Big Bang. The gravitational wells those seeds created had to be deep enough to pull in staggering amounts of gas with breathtaking speed, initiating a feeding frenzy that broke all the polite rules of physics. This timeline is not a suggestion, it is a mandate written in the mass of these silent titans, forcing us to rewrite the story of the universe's infancy with a new, urgent tempo. The silent partner in this cosmic violence is a force we cannot see. While gravity pulls matter inward, another power, equally immense, channels and directs the chaos. Around these ancient black holes, magnetic fields are not gentle guides, but titanic structures woven into space itself. They are born from the churning, superheated plasma of the accretion disk, where charged particles swirl in a frenzied dynamo, amplifying magnetic lines until they become cosmic ropes of pure energy. These fields do not just exist, they dominate. They are the invisible architecture that sculpts the black hole's most spectacular outputs. Picture the magnetic field lines as if they were rigid wires frozen into the spinning disk. As the black hole and its disk rotate, these lines are dragged and twisted into a colossal, spiraling funnel. This twisted magnetic funnel becomes the particle accelerator for the relativistic jets. Charged particles, electrons and protons, get caught on these lines like beads on a wire and are slung outward at nearly the speed of light, focused into those narrow, devastating beams that scream from the black hole's poles. Without these unimaginably strong magnetic fields, the jets would never form. The energy would simply dissipate into a shapeless cloud, but the magnetic field's role goes even deeper. It acts as a cosmic brake, a way for the black hole to shed its own furious spin. As the field lines twist, they create resistance against the black hole's rotation, effectively slowing it down over eons. The rotational energy that is lost does not simply vanish. It is transferred outward, powering the jets and adding to the intense radiation from the disk. This process, known as the Blandford-Zenagic mechanism, shows that the magnetic field is a two-way street. It both extracts energy from the black hole's spin and uses that energy to project its influence across the universe. Furthermore, these magnetic fields dictate the very rhythm of the feast. They control how efficiently matter in the accretion disk spirals inward, creating turbulence and friction that heats the gas to its incredible temperatures. They can even lift material off the disk's surface, contributing to the powerful outflows that regulate the black hole's growth. In the end, the magnetic field is the great conductor of this cosmic orchestra. Gravity provides the stage and the players the swirling mass of gas and dust. but it is the magnetic field that directs the performance, deciding where the energy goes, shaping the jets, and ultimately determining how the black hole's furious power is broadcast into the void. That magnetic field orchestrates a reality we can measure, but our observations rest on a deeper, more unsettling truth. The brilliant quasar we see blazing from the edge of the cosmos is not a current event. It is a fossil of an event that concluded billions of years ago. The light from these most distant black holes is a message from a past so deep that the object itself may no longer exist in the form we perceive. This is the profound strangeness of looking across the universe. We are watching a movie of the cosmos, but the film is so long that the actors may have left the stage long before we see their opening scene. Consider a specific, mind-bending possibility. One of these ancient, brilliant quasars might have been powered by two supermassive black holes spiraling toward a cataclysmic merger. We see them as separate, shining cores in our data, a snapshot of their orbital dance from 13 billion years ago. But in the time it has taken that snapshot's light to crawl across the universe to us, those two black holes have almost certainly already collided. The titanic burst of gravitational waves from that merger, the formation of a single, even larger monster, and the subsequent quieting of the quasar as the new black hole settled down, all of that is history. It is over, yet to our eyes and instruments, the pre-merger spectacle is still playing out. We are watching the opening act of a play whose finale happened before our planet even formed. This principle extends to an even more exotic idea. Some theories suggest the very first black holes could have been primordial, formed not from stars but from density fluctuations in the universe's first second. If such a tiny, primordial black hole existed with a low enough mass, a process called Hawking radiation could have caused it to slowly evaporate over billions of years. According to this theory, a small black hole would eventually vanish in a final, faint pop of energy. So it is conceivable, though highly speculative, that a point of light we detect as a primordial black hole from the cosmic dawn might have evaporated entirely eons ago. We would be seeing the ghost of an object that has already faded from existence. This is not science fiction. It is a direct consequence of the finite speed of light and the vastness of cosmic time. The universe's most distant beacons are therefore more than just time capsules. They are cosmic echoes, images of events so profoundly past that their present reality is forever separated from us by an unbridgeable sea of years. We map the heavens not as they are, but as they were, forever chasing the afterimage of creation. The search for these cosmic echoes is not confined to the silent domes of professional observatories. It has spilled out into the world, onto the computer screens of ordinary people, transforming the hunt into a global, collaborative effort. This brings us to a beautiful truth about modern astronomy. Some of the most unusual and distant quasars have been found not by a lone scientist, but by a global community of volunteers. Projects like Galaxies have fundamentally changed how we sift through the universe's data. The concept is elegantly simple. Telescopes like the Sloan Digital Sky Survey capture images of millions upon millions of celestial objects. No single research team could ever hope to visually inspect them all. So, astronomers turn to the most powerful pattern recognition system on the planet, the human brain. They created a website where anyone, anywhere could log on and be shown an image of a galaxy. The task is straightforward: classify its shape. Is it a spiral, an elliptical, or something else? This simple act of looking and clicking becomes a critical first filter. Most volunteers will see normal, nearby galaxies, but every so often, someone will be presented with a tiny, puzzling red dot that looks like nothing else. It might be a star in our own galaxy, or it might be a quasar from the edge of time. These unusual objects get flagged for further professional investigation. The power of this approach is staggering. Hundreds of thousands of eyes working together can process volumes of data that would overwhelm any algorithm. The human mind is exceptionally good at spotting the odd, the unusual, the thing that just doesn't fit. In one famous case, a Dutch schoolteacher named Hanny van Arkel, participating in Galaxy Zoo, noticed a strange greenish cloud of gas near a galaxy. This object, now known as Hanny's voorwerp, turned out to be a luminous echo of a quasar that had recently shut off, a fossil of light from a dead monster. Discoveries like this, made by curious individuals at home, have directly contributed to our understanding of quasars and their life cycles. It means that the light from a black hole that shone 13 billion years ago might first be noticed by a teacher on a lunch break, a student after homework, or a retiree with a passion for the cosmos. This democratization of discovery reminds us that the universe belongs to everyone. The map of the most distant black holes is being charted not just by satellites and supercomputers, but by a quiet, worldwide network of human curiosity, one galaxy at a time. Human curiosity can only flag the anomalies we can see. The greatest monsters from the cosmic dawn might be hiding in plain sight, their light completely transformed by the very chaos of their birth. The most distant black hole of all, the true first of its kind, could be invisible to the very surveys that have found its slightly younger cousins. This is because the universe's earliest, most gas-rich galaxies were not clean, transparent places. They were chaotic nurseries, thick with the dust and gas of furious star formation. Imagine a newborn supermassive black hole at the heart of such a place. It begins to feed, its accretion disk blazing with ultraviolet light, but that brilliant radiation cannot escape. It slams into the dense, dusty cocoon of material still collapsing around the young galaxy's core. The ultraviolet and visible light are absorbed completely, their energy transferred to the surrounding dust grains. Those dust grains, now heated to a few hundred degrees, do not re-radiate the energy as light we can see. They glow with a deep, warm heat, emitting their energy in the far infrared and submillimeter wavelengths. To an optical or even near-infrared telescope, this object would be a dark spot, a shadow within a shadow. Its power is not in a piercing beacon, but in a diffuse, warm whisper. This is the realm of the dust-obscured supermassive black hole, a hidden giant whose brilliance is smothered by its own cradle. Finding them requires a different kind of vision, one that sees not starlight, but the gentle heat of cosmic soot. This is where our newest, most powerful instruments become essential. The James Webb Space Telescope, with its unmatched sensitivity in the mid-infrared, can peer into these dusty hearts, detecting the specific chemical signatures of warm molecules and heated dust that betray the hidden monster within. But to see the coldest, most extended dust, we need to listen to a different part of the spectrum entirely. Enter ALMA, the Atacama Large Millimeter/Submillimeter Array, a vast collection of radio dishes high in the Chilean desert. ALMA does not see light as our eyes do. It detects millimeter and submillimeter waves, the domain of cold gas and the faint thermal glow of dust just a few tens of degrees above absolute zero. ALMA can map the distribution of cold dust and gas swirling around a hidden quasar, tracing the furious winds and outflows even when the central engine is completely veiled. Together, Webb and ALMA act as complementary detectives. Webb might identify a distant galaxy that is anomalously bright in the infrared but dark in all other colors, a prime suspect for harboring a shrouded quasar. ALMA can then examine that suspect, analyzing the cold material around it to measure its mass, its motion, and the powerful forces at play. Their mission is to lift the cosmic veil, to find the black holes that did not blaze as clear lighthouses, but instead simmered as hidden furnaces, their growth and influence shrouded in the primordial dust of creation. The true record holder for the most distant black hole may not be a brilliant point in our databases yet. It may be a faint, warm smudge in the data, waiting for these tools to translate its muffled story into our understanding of the dawn. These cosmic furnaces, hidden or blazing, represent the ultimate gravitational laboratories. the supermassive black holes from the cosmic dawn do more than challenge our timeline. They press against the very laws of physics that govern reality. Einstein's theory of general relativity has been our gold standard for understanding gravity for over a century, describing it not as a force but as the curvature of space-time by mass and energy. It predicts everything from the bending of starlight to the existence of black holes with stunning accuracy. Yet, in the hearts of these most distant, most massive objects, where gravity reaches its absolute extreme, we might finally find the cracks in this magnificent framework. General relativity is a theory of the very large, but it famously does not play well with quantum mechanics, the theory of the very small. To find a unified theory of quantum gravity, a single rulebook for the entire cosmos, we need to observe gravity in conditions so severe that any subtle deviation from Einstein's predictions would become visible. The environment around a billion solar mass black hole in the infant universe is precisely such a place. Here, space-time is not just curved, it is wound into a knot, spinning at nearly the speed of light, surrounded by plasma heated to trillions of degrees, and embedded in a universe that was far denser and more dynamic than it is today. It is a crucible where the fundamental nature of reality was tested under conditions we can never hope to recreate on Earth. By studying the light from these ancient quasars, the orbits of gas in their accretion disks, and the echoes of their immense power, we are not just doing astronomy. We are conducting a fundamental physics experiment on a cosmic scale, using the universe's first monsters as our apparatus. Any anomaly in their behavior, any detail in their spectra that does not match the predictions of pure general relativity, could be the first whisper of a deeper truth. It might hint at extra dimensions, at the quantum nature of space-time itself, or at modifications to gravity that only manifest in the most intense gravitational fields. These distant black holes are the universe's most rigorous and unforgiving professors, teaching us that to understand the force that binds the cosmos, we must look to its very edge and its very beginning. The very fabric of space-time around these ancient monsters is not merely curved, it is violently stirred. This leads to a prediction so strange it sounds like science fiction, but it is rooted in the hard mathematics of general relativity. The accretion disks feeding these distant black holes might not be flat, orderly platters of gas. They could be profoundly warped, twisted into shapes like a cosmic potato chip or a broken record. The culprit is a phenomenon known as frame dragging. When a black hole spins, it does not just rotate like a planet. Its immense mass and angular momentum literally drag the fabric of space-time around with it, like a spinning spoon in a thick fluid. This effect is strongest near the event horizon, in the inner regions of the accretion disk where matter is whirling at its most frenzied pace. There, the dragging of space-time becomes so extreme that it can overpower the natural tendency of the disk to flatten into a plane. Different parts of the disk, orbiting at different distances, get pulled in different directions by this twisted space-time geometry. The result is a warped disk where the inner region tilts and precesses independently of the outer regions. It is as if the innermost track of a vinyl record was bent upward while the outer tracks remained flat, creating a chaotic, wobbling structure. This is not a minor detail. A warped disk has dramatic consequences for how we see the quasar. A flat disk presents a relatively consistent face to us as it spins, but a warped, wobbling disk presents a constantly changing surface area and angle to our line of sight. As different, hotter inner regions tilt toward and away from us during its rotation, the overall brightness of the quasar would flicker in a complex, unpredictable pattern. This could explain some of the strange, erratic variability we see in the light curves of the most distant quasars, a variability that simple models of flat disks cannot fully account for. Furthermore, the warping can cause parts of the disk to cast shadows on other parts, or for radiation to be funneled in specific directions, making the quasar appear brighter or dimmer from certain vantage points in the cosmos. This means the brilliant beacon we rely on to see across the universe is not a steady, uniform lighthouse. It is a guttering, twisted torch, its flame distorted by the very vortex of space-time that feeds it. The chaotic magnetic fields around these ancient black holes might be responsible for flashes of energy that reach us from across the cosmos. A new and mysterious cosmic signal has emerged in recent years, one that holds a potential, though entirely speculative, link to the monsters from the dawn of time. These are fast radio bursts, or FRB. An FRB is exactly what it sounds like, a burst of radio waves that appears in our telescopes as an incredibly bright, incredibly brief flash. It lasts only a few thousandths of a second, yet in that fleeting moment, it can release more energy than our sun does in 80 years. Their origin is one of the greatest puzzles in modern astronomy. Some FRBs are one-off events, while others repeat in unpredictable patterns. We have traced a few to distant galaxies, but the exact engine that creates them remains hidden. This is where the speculative connection to ancient black holes begins. One compelling theory suggests that certain types of FRBs could be born in the intensely magnetized environments around supermassive black holes, particularly those that are rapidly spinning. Picture the scene near the event horizon of such a titan. The magnetic field lines are not static. They are constantly being wound up, twisted, and stretched by the black hole's furious rotation and the churning plasma of the accretion disk. This creates titanic tension, like winding a rubber band tighter and tighter. According to some models, these magnetic fields can suddenly snap and reconnect in a catastrophic event. When they do, they release an enormous amount of energy in an extremely short time, accelerating particles to near light speeds. This sudden, violent release could manifest as a brilliant, coherent blast of radio waves, a fast radio burst. The scale fits. The energy required for the most powerful FRBs is staggering, and few cosmic engines can provide it. A supermassive black hole in a feeding frenzy certainly can. Furthermore, if the black hole is surrounded by a thick, dense torus of gas and dust, the radio burst might need to fight its way out, explaining why some FRBs show signs of having traveled through a dense, magnetized environment. The repeating nature of some bursts could be explained by a periodic process, like the wobble of a warped accretion disk or the orbital motion of a companion object, triggering these magnetic snapshots at regular, though unpredictable, intervals. It is a tantalizing idea that a millisecond flash of radio noise detected by a telescope on Earth could be the final, twisted scream of a magnetic field line snapping near a black hole that formed when the universe was in its infancy. While no definitive link has been proven, and many FRBs likely have other origins like magnetars, the possibility remains open. It suggests that the influence of the most distant black holes might not be confined to the ancient light we study. Their violent magnetic ghosts could still be reaching us today in sudden, brilliant whispers on the radio airwaves of the cosmos. The brilliant beacons of the early universe are not scattered like random stars in a night sky. Their placement is deliberate, a grand design written in gravity and light. The most distant quasars are not evenly distributed across the cosmos. Instead, they cluster together in vast, sweeping patterns, tracing the invisible architecture of the infant universe. This clustering is not an accident of observation. It is a direct reflection of the underlying cosmic web, the skeleton of dark matter upon which all visible structure is hung. In the universe's youth, dark matter, that mysterious, invisible substance, had already begun to clump under its own gravity, forming an immense three-dimensional network of filaments and nodes. Ordinary matter, the gas that would form stars and galaxies, simply followed this gravitational blueprint, flowing into the deepest wells of dark matter. The very first, most massive black holes ignited in the densest of these nodes, the richest intersections of the cosmic web. So, when we map the positions of hundreds of these ancient quasars across billions of light years, we are not just plotting points of light. We are drawing the outlines of the cosmic web as it existed over 13 billion years ago. Their clustering reveals where the gravitational peaks were, showing us the large-scale structure of the universe in its adolescence. It is a map of potential, a snapshot of the universe's scaffolding at a time when galaxies were just beginning to crystallize within it. This pattern tells a profound story. The universe did not build itself uniformly. It grew from specific seeds, and the most powerful engines of that growth, the distant quasars, mark the locations where the construction of our modern cosmos was most intense. The cosmic dance of merging black holes faces a profound and stubborn obstacle. After two galaxies collide, their supermassive black holes are drawn together by gravity, spiraling toward a cataclysmic union. But this process can grind to a halt. As the black holes draw closer, they clear out the stars and gas from their immediate vicinity, effectively robbing themselves of the very material that helps them lose orbital energy and spiral inward. At a separation of about 1 parsec, which is roughly 3.26 light-years, they can simply stall. This is the final parsec problem, a theoretical wall that suggests binary supermassive black holes might never actually merge within the age of the universe. It is a cosmic standoff where two titans are forever locked in a gravitational embrace, unable to take the final, fatal plunge. This puzzle is critical because if mergers are impossible, then our models for how the very first black holes grew so massive so quickly are in serious trouble. Yet, the early universe was a very different place. The solution to the final parsec problem may lie in the unique, chaotic conditions of the cosmic dawn. Back then, galaxies were smaller, denser, and packed with gas. When two such galaxies merged, their central black holes would not be orbiting in a near vacuum. They would be swimming through a thick, turbulent sea of stars, gas, and dark matter. This dense environment provides the friction needed to keep the merger going. A third black hole from another minor merger could be flung into the system, transferring energy and kicking the stalled pair closer together in a process called a gravitational slingshot. Or the vast, gas-rich disks surrounding the young black holes could interact, creating drag that continuously saps their orbital energy. In the infant cosmos, the final parsec was not a barren no-man's land, but a crowded, dynamic arena where gravity always found a way to finish the job. This means the violent mergers we suspect built the first giants were not only possible, they were likely inevitable, driven by the sheer density and chaos of the universe's first chapters. The gold in your jewelry may have been forged in the heart of a cosmic catastrophe. The violent environments around the most distant black holes are more than just engines of destruction. They are potential cosmic forges, factories for creating the heaviest elements in the universe. Inside stars like our Sun, nuclear fusion builds elements up from hydrogen to iron, one atom at a time. But to create anything heavier than iron, like gold, platinum, or uranium, you need a far more extreme process. You need a flood of free neutrons, subatomic particles with no electrical charge, to bombard atomic nuclei before they have a chance to decay. This is called the rapid neutron capture process, or the R process. For decades, astronomers believed the primary site for the R process was the cataclysmic merger of two neutron stars, the ultra-dense cores left behind by supernova. But there is a problem with that timeline for the early universe. Neutron star mergers are rare events, and they take time to occur. The first generation of stars had to die, leave behind neutron stars, and then those neutron stars had to spiral together over eons. Yet, we see evidence of heavy R process elements in some of the oldest stars in our own galaxy, stars that formed when the cosmos was still young. This suggests that another, faster pathway to creating these elements must have existed in the universe's infancy. Enter the ancient quasar. Its relativistic jets and powerful outflows provide a staggering alternative. Imagine the base of one of those jets, where magnetic fields accelerate particles to nearly the speed of light and temperatures soar to trillions of degrees. In this maelstrom, nuclei are torn apart, creating a dense soup of free neutrons and protons. As this material is blasted outward in the jet or the spherical wind, it expands and cools rapidly. In that brief window of cooling, neutrons can be captured by seed nuclei at an incredible rate, building up gold, uranium, and other rare earth elements in a matter of seconds. This is a factory operating at a scale we can barely comprehend. A single quasar outburst could seed its entire host galaxy and the surrounding intergalactic space with a spray of these newly minted heavy elements. The next generation of stars that form from this enriched gas would then contain the fingerprints of that ancient cataclysm. So, the most distant black holes might have done more than clear the cosmic fog and shape galaxies. They could have been the universe's first alchemists, transforming the primordial simplicity of hydrogen and helium into the complexity of gold, and doing it at a time when the cosmos was still taking its first breaths. This stretching of light across the cosmos has a strange twin effect, one that warps our very perception of time itself. When we observe a sudden event from the edge of the universe, like a brilliant flare erupting from the accretion disk of a distant quasar, we are not seeing it play out in real time. We are watching it in slow motion. This is a direct consequence of the universe's expansion, a phenomenon known as cosmological time dilation. The principle is tied directly to the redshift we've discussed. Remember, the expansion of space stretches the wavelengths of light, making them redder, but it does more than that. It also stretches the very intervals between the arrival of those light waves. Think of the light from that distant quasar not as a continuous beam, but as a series of distinct pulses like the ticks of a cosmic clock. Each tick is a photon carrying information. As space expands during the photon's journey, the distance between successive ticks gets stretched, just like the wavelength of the light itself. This means the ticks arrive at our telescopes farther apart than they were emitted. If the quasar's clock ticks once per second in its own frame of reference, by the time those ticks reach us, they might be arriving once every 10 seconds. A process that took 10 days to unfold in the vicinity of the black hole. A flare building, peaking, and fading would therefore be observed by us over a period of 100 days. It is as if we are viewing the universe's most violent fireworks through a temporal lens that slows everything to a crawl. This isn't just a theoretical curiosity. It has practical consequences for how we interpret the data from these ancient objects. The flickering and variability we detect in a quasar's brightness, which we use to understand the physics of its accretion disk, are all stretched out. A rapid, chaotic flicker that would tell us about instabilities in the disk near the event horizon is smoothed into a gentle, slow undulation by the time it crosses the cosmic void. To understand the true, frantic tempo of the early universe, astronomers must account for this dilation, mathematically compressing our observed timeline back to what it must have been in that distant, younger cosmos. It is a final, profound layer of separation between us and these titans. We see them not only across an impossible gulf of space, but through a slow, thick syrup of expanded time, their most furious moments rendered as patient, drawn-out sighs. This slow-motion view of the cosmos is about to be shattered by a new kind of eye on the sky. A revolution in our understanding of the most distant black holes is poised to begin, not with a single, deep stare into the void, but with a relentless, all-seeing gaze. The Vera C. Rubin Observatory, currently under construction in the clear, dry mountains of Chile, represents a fundamental shift in how we will map the dynamic universe. Its core mission is the Legacy Survey of Space and Time, or LSST. For 10 years, this observatory will perform an unprecedented task. It will scan the entire southern hemisphere sky every few nights with a camera the size of a small car, capturing the most detailed cinematic portrait of the cosmos ever made. Where current telescopes might study a few thousand distant quasars in depth, the LSST will detect tens of millions. It will find them not by targeting specific red dots, but by simply watching everything everywhere all at once. The power of this approach lies in change. The universe is not a static painting. It is a living, breathing entity. Quasars flicker, they flare, they erupt. By comparing each night's new image with the last, the ULAS powerful software will flag anything that has varied in brightness. A distant quasar that was too faint to notice in a single snapshot will betray itself by its telltale flicker over weeks and months, its variability a dead giveaway against the backdrop of steady stars. This will pull ancient black holes out of the darkness by the thousands, many of them too faint or too obscured for our current surveys to have ever spotted. But the ULAS true magic lies in capturing the rare and the sudden. It will be an unparalleled watchman for cosmic catastrophes happening at the edge of time. Imagine a star wandering too close to a supermassive black hole in a galaxy 13 billion light-years away. The black hole's tidal forces will stretch and shred the star in a violent event known as a tidal disruption flare. For a few brief months, that distant galaxy's core will blaze with incredible intensity as the stellar debris rains down onto the accretion disk. Today, we catch only a handful of these events in the nearby universe. The ULAS, with its nightly patrol of the entire sky, will catch them happening at phenomenal distances, turning the momentary death screams of stars into beacons that reveal black holes in galaxies otherwise too quiet and faint to detect. It will witness the ignition of newborn quasars as galaxies merge, and track the slow, rhythmic flickers that might betray the orbital dance of binary black holes from the cosmic dawn. The Vera Rubin Observatory will not just give us a deeper snapshot of the early universe. It will give us its first full-length movie, revealing the violent, dynamic lives of the first monsters in a way we have never seen before. A black hole's ultimate simplicity is captured by a famous, almost poetic idea in physics. It is called the no-hair theorem. This is not about literal hair, of course, but about information. The theorem states that a black hole, for all its terrifying complexity and the chaotic history of everything that fell into it, can be completely described by just three numbers: its mass, its spin, and its electric charge. Every other detail, the chemical composition of the stars it consumed, the shape of the galaxies it tore apart, even the identity of the matter itself, is lost forever behind the event horizon. The black hole has no hair, no distinguishing features beyond those three bald facts. It is the universe's ultimate eraser, creating a perfectly smooth, featureless silence from unimaginable violence. This elegant idea is a cornerstone of our understanding, but like all theories, it must be tested in the most extreme laboratories nature can provide. And there is no environment more extreme than the supermassive black holes from the cosmic dawn. These ancient monsters, growing at breakneck speeds in a dense, primordial universe, represent a set of conditions we can never replicate. Their immense gravity, their furious spin, and the searing plasma around them push physics to its absolute limit. By studying the light from their accretion disks and the echoes of their powerful jets, we are not just looking back in time. We are conducting a fundamental experiment. Any tiny, persistent anomaly in their behavior, a flicker of light that doesn't match predictions, a subtle distortion in the spectrum that can't be explained by mass, spin, and charge alone, could be a whisper of something more. It could be a hint that information is not entirely lost, that black holes might, in some subtle way, retain a memory of their past. They might, in the poetic language of physics, have a faint shadow of hair after all. Proving or disproving this with observations from the edge of time is a staggering challenge, but it is the kind of challenge that reshapes our understanding of reality itself. The most distant black holes are not just fossils, they are the universe's most rigorous professors, testing the laws of physics under conditions so severe they might finally reveal a deeper, more complex truth hiding within the apparent simplicity of the void. The universe's first giants could not have grown from nothing. To solve the paradox of their impossible size, we must search for a middle step, a cosmic adolescent in the black hole family tree. This is the hunt for intermediate mass black holes, objects with masses ranging from a few hundred to a few 100,000 times that of our Sun. They are the crucial missing link, the potential stepping stones between the small seeds left by the first stars and the billion solar mass titans that shone from the cosmic dawn. If supermassive black holes grew by steadily feasting, they needed a substantial meal to start with. A stellar mass black hole of 10 suns, accreting at the maximum theoretical rate, would struggle to reach a billion suns in just a few 100 million years. But an intermediate mass black hole, a seed of 10,000 or 100,000 solar masses, provides a colossal head start. It is the difference between trying to build a skyscraper by stacking bricks one by one and starting with the foundation and first 10 floors already in place. The existence of these intermediate monsters in the early universe would neatly bridge the gap in our timeline, turning an impossible sprint into a plausible, though still frantic, race. Yet for all their theoretical importance, intermediate mass black holes remain profoundly elusive, especially at the edge of time. Their nature makes them perfect ghosts. They are too massive to form from a single collapsing star, yet not massive enough to power the brilliant, galaxy-dominating quasars that act as our beacons across cosmic distances. An intermediate mass black hole feeding quietly in a small, early galaxy would be a faint smudge, incredibly difficult to distinguish from a cluster of bright stars or a small, star-forming galaxy. Our current telescopes simply lack the resolution to pick out such a specific, faint object from 13 billion light-years away. So the hunt becomes indirect, a search for subtle cosmic signatures. One promising method looks for the telltale flicker of stars. If an intermediate mass black hole lurks at the heart of a dense, ancient star cluster, its gravity will influence the motions of the surrounding stars. They will orbit faster, whipping around an invisible point, their speeds betraying the mass of the hidden anchor. We see hints of this in some globular clusters within our own Milky Way, where stars move as if tugged by something dark and heavy. Another clue comes from flickering X-rays. Occasionally, an intermediate mass black hole might tear apart and consume a passing star or a small gas cloud. The resulting flare of X-rays, while brief, would be distinct from the signal of a smaller stellar black hole or a larger quasar. Spotting such a transient flash from the early universe is like waiting for a single, specific firefly to blink in a distant forest during a thunderstorm, but it is possible. Future observatories with wider fields of view and rapid alert systems may finally catch these events. The discovery of even one intermediate mass black hole from the cosmic dawn would be a transformative moment. It would confirm a critical chapter in the life story of the universe's greatest monsters, revealing the middle step in their journey from obscure seed to cosmic sovereign. The spectrum of a distant quasar is more than a fingerprint. It is a layered history of the universe itself. As that ancient beam of light travels toward us, it does not move through empty space. It passes through the sparse, diffuse gas that fills the vast voids between galaxies, the very material of the cosmic web. And as it does, atoms within that gas leave their mark. Hydrogen, helium, and the first heavy elements like carbon and oxygen absorb very specific wavelengths of the quasar's light, depending on their chemical composition. Each cloud of gas at a different distance along the line of sight creates a dark absorption line in the final spectrum we receive. But because the universe is expanding, each cloud is also moving away from us at a different speed. This stretches each absorption line by a different amount. The result is not a single dark line, but a dense forest of them, a picket fence of shadows stretching across the rainbow of the quasar's light. Each picket in that fence corresponds to a specific cloud of gas at a specific moment in cosmic history. By reading this pattern, astronomers can perform a kind of cosmic archaeology. They can determine not just what elements exist in the intergalactic medium, but when those elements appeared. The very first absorption lines, those from clouds closest to the quasar in both space and time, show only hydrogen and helium, the pristine elements forged in the Big Bang. But as you look at lines from clouds progressively closer to us, which means from later cosmic eras, a change occurs. New, heavier elements begin to appear in the pattern. You start to see the faint fingerprints of carbon, silicon, and oxygen. This is the record of enrichment, the universal history written in gas. Those heavier elements were not present at the beginning. They were forged in the nuclear furnaces of the first generations of stars and then blasted into space by supernova explosions. That enriched material mixed with the primordial gas, polluting it with the building blocks of planets and life. The quasar's light, acting as a probe, sampled this changing mixture across billions of years. So, a single spectrum from one distant black hole contains a timeline of cosmic chemistry. It tells us when the first stars lived and died, how quickly they seeded the void with new elements, and how that enrichment spread through the expanding cosmos. We are not just looking at a monster's beacon, we are reading the autobiography of the universe, written in the shadows cast upon its oldest light. Forget the idea of a galaxy giving birth to a black hole. The most ancient monsters might have built their own homes from scratch. This flips the entire cosmic narrative on its head. Our standard story is straightforward. First, a vast cloud of gas collapses to form a galaxy, and then, over eons, a black hole grows at its center. But the impossible size of the earliest supermassive black holes forces us to consider a radical alternative. What if the black hole came first? Imagine a single, massive seed, perhaps a primordial black hole born from the universe's first chaotic moments, or a direct collapse monster from a pristine gas cloud. This seed would be an anchor of immense gravity in an otherwise smooth, expanding sea of hydrogen. Its powerful gravitational pull would act like a cosmic magnet, drawing in the surrounding gas from vast distances. This infalling gas would not just feed the black hole, it would also begin to swirl and compress around it, creating the perfect conditions for the first stars to ignite. A whirlpool of star formation would erupt around this dark heart, and over millions of years, that swirling, shining structure would become the galaxy itself. In this scenario, the black hole is not a consequence of galactic evolution. It is the cause. It is the nucleus around which the entire celestial city crystallizes, the gravitational keystone laid down before the first walls were ever raised. The monster does not move into a pre-built palace. It grows the palace around itself, stone by stellar stone, from the raw materials its own gravity collects. This idea solves the timing paradox elegantly. The black hole gets a colossal head start, beginning its growth the instant the universe allows, and its very presence orchestrates the assembly of the stars that will become its host. We are left with a profound reimagining of cosmic origins, where the darkest objects in existence are not the final products of creation, but its very first architects. This relentless search for first light brings us to an absolute, unbreakable wall. There is a fundamental limit to how far back we can see, a horizon in time beyond which not even the most powerful telescope will ever peer. That limit is set not by our technology, but by the very state of the infant universe itself. We can search for black holes from the first few 100 million years, but we will never see one from the first 380,000 years. The reason is etched across the entire sky in a faint, cold glow, the cosmic microwave background, or CMB. This is not the light of the first stars or quasars. It is the afterglow of the Big Bang itself, the moment the universe became transparent. To understand why this is a wall, we must go back to that primordial fog. For the first several 100,000 years after the Big Bang, the cosmos was a seething, opaque plasma. Protons and electrons were separate, free particles, and light photons could not travel more than a tiny distance before being scattered by this dense, charged soup. The universe was a brilliant, blinding fog filled with light but with no clear lines of sight. Then, as expansion cooled the cosmos, a pivotal transition occurred. The temperature dropped enough for protons and electrons to combine into neutral hydrogen atoms. Suddenly, the charged particles that scattered light were gone. The fog lifted, the universe became transparent. That first flash of light released from the plasma in every direction has been traveling ever since. Stretched and cooled by 13.8 billion years of cosmic expansion, it now reaches us as a uniform microwave whisper, just a few degrees above absolute zero. This is the cosmic microwave background. It is the oldest light we can possibly detect, a snapshot of the universe at the tender age of 380,000 years. And it creates an impenetrable curtain. Any object, any event, any black hole that existed before this moment is forever hidden behind this wall of primordial light. The photons from such an object could not travel freely through the opaque plasma. They would have been scattered, absorbed, and re-emitted countless times, their original information utterly scrambled and lost. Even if a primordial black hole formed in the universe's very first second, its influence is trapped behind this glowing veil. We can infer its possible existence through its gravitational effects on later structures, but we will never receive a direct photon from it. The CMB is therefore both our greatest gift and our ultimate boundary. It provides the clearest baby picture of the cosmos, confirming the Big Bang and giving us a detailed map of the seeds that would grow into galaxies. But it also marks the end of the line for direct observation. The most distant black holes we chase are those that switched on just after this great clearing, their light the first to travel freely through the newly transparent cosmos. They shine from the near side of this final wall, the oldest beacons we are ever destined to see directly. The most distant black holes are already pushing our greatest observatories to their absolute limits. To see further, to hear their faintest whispers, we must dream of instruments that do not yet exist. The quest to understand these ancient monsters is actively inspiring the blueprints for the next generation of cosmic explorers. Telescopes so ambitious they redefine the very meaning of observation. Consider the gravitational waves from the mergers of the first supermassive black holes. That deep, low-frequency rumble in the fabric of space-time is completely invisible to our current ground-based detectors. To hear this ancient chorus, we need an observatory of a different kind, one built not on rock, but in the perfect silence between worlds. This is the vision behind the Laser Interferometer Space Antenna, or LISA. Imagine 3 spacecraft flying in a vast triangular formation millions of miles apart, connected only by lasers. Their mission is to measure the microscopic stretching and squeezing of the space between them caused by passing gravitational waves. LISA will be tuned to the low-frequency waves produced by the mergers of billion solar mass black holes, the very collisions we suspect built the giants of the cosmic dawn. It will not see light. It will listen to the vibrations of space-time itself, detecting the final, violent moments of unions that occurred when the universe was in its infancy. The data will be a soundtrack to creation, a direct recording of the most energetic events since the Big Bang, revealing the population, the masses, and the spin of the very first black holes in a way light alone never could. But our ambitions reach even further than listening. To truly witness a black hole's shadow, the dark silhouette cast against the glowing gas of its accretion disk, we have performed a miracle of engineering with the Event Horizon Telescope, linking observatories across the globe to create an Earth-sized virtual dish. Yet that image is of a nearby modern black hole. To see the shadow of a quasar from the edge of the universe, to watch how that shadow and its surrounding ring of light change over billions of years as the black hole evolves, we would need a telescope of unimaginable scale. Scientists are already sketching concepts for colossal optical and infrared telescopes built in the permanent shadow of the moon. or vast arrays of spacecraft flying in precise formation to create an interferometer with a baseline not of thousands of miles but of millions. These future eyes would do more than take a snapshot. They would create a time-lapse film of cosmic history, tracking how the monsters of the dawn matured, how their feeding habits changed, and how their immense gravity warped the light around them across eons. Each new discovery about these distant black holes creates a new question, and each question demands a new tool. They are not just subjects of study. They are the architects of our future, compelling us to build ever grander windows to the past, ensuring that the final chapter of their story has not yet been written. Their light is a 13 billion-year journey, a message from a time before Earth existed. To stand beneath a clear night sky and know that some of those faint, steady points are not stars, but the final, stretched glow of monsters that ruled infant galaxies, is to feel a profound and humbling shift in perspective. These distant black holes are not merely scientific curiosities. They are cosmic historians, forcing a confrontation with scales that defy human intuition. They show us a universe that was dynamic, violent, and brilliantly luminous long before our solar system was even a whisper in the void. Our entire recorded history, every empire that has risen and fallen, every human life ever lived, fits into a mere sliver of the time it has taken for that ancient light to finally reach our eyes. This temporal scale crushes any notion of cosmic centrality. We are not the purpose of this story. We are a very late, very small footnote in a narrative that began with energies and scales we can scarcely comprehend. These black holes remind us that the cosmos operates on a stage of almost unimaginable grandeur and duration, governed by laws that are indifferent to our hopes, our fears, and our fleeting presence. Yet within that indifference lies a strange beauty. We are the part of the universe that has become conscious, that has built tools to reach back across the eons and decode the light from its own violent childhood. The very act of studying these distant giants is a testament to a profound curiosity that emerged from stardust, reaching out to understand its own origins. It is a dialogue between the universe's youngest, most fragile thinkers and its oldest, most powerful engines. This perspective does not diminish us. It recontextualizes our existence. We are not the center, but we are witnesses. We are the universe awakening to contemplate itself, using the faint, ancient whispers of its first monsters to piece together the epic of its own birth. That is a privilege as staggering as the distances involved. Our current view of the cosmic dawn is based on a handful of extreme outliers. The brilliant quasars we have detected are the freaks, the 1% of the 1% from that era. They are the loudest, brightest, most gluttonous monsters in a universe that was, for the most part, still dark and quiet. We have been listening for a whisper and have only heard the shouts. This means our entire understanding of the first billion years is built upon a profoundly biased sample. It is as if future archaeologists trying to understand life in the 21st century had only a few volumes on the lives of kings and tycoons, with no record of the ordinary towns, the quiet villages, or the vast, empty countryside. We know the kings existed and their power was immense, but we have no idea how many subjects they ruled, or what daily life was like for the common people of the early cosmos. The James Webb Space Telescope is our tool to correct this bias. Its unprecedented infrared sensitivity is not just for finding fainter versions of the same brilliant quasars. It is designed to find the quiet ones. It will see the host galaxies of those quasars in stunning detail, finally showing us the full context of their reign. But more importantly, it will find the smaller, dust-shrouded, or simply less voracious black holes that were always there, hidden in the shadows of the giants. These are the commoners of the cosmic dawn, the growing black holes in small, early galaxies that did not have the constant, rich fuel supply to become brilliant beacons. By finding them, Webb will allow us to take a true census. We will begin to answer fundamental questions. What fraction of early galaxies hosted a central black hole? How did their masses typically compare to their host galaxies? Did every galaxy start with a seed, or was it a privilege of the densest environments? This shift from studying rare outliers to mapping the full population is a revolution in the making. It transforms the field from a study of spectacular anomalies to a proper science of demographics. And Webb is just the beginning. The upcoming Nancy Grace Roman Space Telescope, with its field of view 100 times larger than Hubble's, will perform wide, deep surveys, finding thousands of these objects and placing them in the grand tapestry of the cosmic web. Future gravitational wave observatories like LISA will listen for the mergers we cannot see, revealing the growth history of the silent majority. We are standing at the threshold of a new era in cosmic archaeology. The first 50 facts have been gleaned from the treasure washed ashore, the rare and glittering fragments from a sunken continent. Now we are building the submersibles that will let us dive into the depths and explore that lost world in its entirety. The map of the cosmic dawn is no longer a sketch with a few bold landmarks. We are about to fill in every valley, trace every river, and finally meet all the inhabitants of that distant formative age. The story of the universe's first monsters is not complete. We have merely read the prologue. That journey through 50 facts is not just a catalogue of cosmic trivia. It is a portrait of a universe in its most formative, violent, and brilliant stage. We have followed the light of the most distant black holes from the blinding glare of their accretion disks, through the stretching eons of an expanding cosmos, to the sensitive mirrors of our greatest telescopes. This light has revealed a story of impossible giants born too soon, of magnetic fields that twist space into particle accelerators, and of violent feedback that sculpted galaxies before they were fully formed. It is a narrative where darkness is not an end but a beginning. The gravitational anchor around which the first structures of reality coalesced. These ancient monsters embody the central themes of cosmic evolution: immense power born from simplicity, growth through catastrophic violence, and a profound mystery that still defies our best models. They are the paradox at the edge of time, challenging us to explain how they could exist at all. Studying them is more than astronomy. It is a test of our deepest understanding of physics, a push against the boundaries of both technology and theory. Every new fact forces us to build a bigger telescope, write a more clever algorithm, and conceive of a more daring idea. This quest, driven by a simple human urge to understand where we came from, has transformed our view of the cosmos from a static backdrop of stars into a dynamic, evolving, and deeply historical entity. The story is far from over. The James Webb Space Telescope is now our primary time machine, its golden eye gathering whispers from the cosmic dawn that will, without doubt, rewrite the chapters we thought we knew. New observatories on the ground and in space, and even in the quiet between worlds to listen for gravitational waves, are being designed right now to answer the questions these 50 facts have raised. So, the next time you find yourself under a clear night sky, look up. Let your gaze travel beyond the familiar stars of our own galaxy, out into the profound black between the constellations. Remember that in that darkness, at the very limit of everything we can see, are the fading afterimages of the universe's first titans. Their story is our origin story. Stay curious, follow the new discoveries as they arrive, and know that in seeking to understand these most distant black holes, we are ultimately trying to understand our own place in the grand, ancient, and astonishingly violent tapestry of existence.